Conservation of mechanical energy. Conservation of mechanical energy states that the total mechanical energy of a system stays constant under certain conditions. First, let's talk about what is mechanical energy. So, mechanical energy is the sum of potential plus kinetic energy. So, PE plus KE is equal to mechanical energy. So, let's review what potential and kinetic energy mean. So, we know that kinetic energy is the energy of motion and it is defined by mass times velocity squared divided by 2. Potential energy, gravitational, is what we want to talk about now. So, potential energy gravitational is the energy by virtue of being in the gravitational field of the earth. And so, it depends on the mass of the object and its position. And it's given by mass times acceleration due to gravity times the height from a chosen reference frame or from the zero potential energy level. So, for a system, the sum of potential and kinetic energy stays constant provided there are no dissipative forces present in the system. If no dissipative or what we call as non-conservative forces, for example, air resistance or friction. So, if these forces are not present, then we can say that the total energy of the system will remain constant. So, what that means is the energy can be converted from potential to kinetic or vice versa, but the total energy always stays the same. What are some examples of conservation of mechanical energy that we see in everyday life? Take the example of a slide. So here is a girl sitting down in she's on the slide. So at the top, if she is at rest, she has potential energy, but no kinetic energy. And as she slides down, because the height increases, the potential energy height decreases, the potential energy decreases, and she gains speed, so the kinetic energy is going to increase. So this is a case of as she slides down, potential energy is being converted to kinetic energy. So let's imagine another example would be a wrecking ball. So a wrecking ball, as it is raised and dropped and it moves to this position and say it's hitting on something. So at the raised position, the ball has potential energy stored in it, and as it moves down, it converts potential to kinetic energy again. Another good example is the roller coaster. So let's take a look at this simulation. So let's put this guy on the top, then hit play. You can see that as the skater rolls down this track, which has a lot of ups and downs, you can see the bar graph showing what happens to the potential energy and the kinetic energy. So let's pause this and do step over step. So as he goes from this position to the bottom of the hill, with the skater at the highest position, let's do slow motion and step forward. Okay, now let's release him from rest. So notice what happens as he comes down in the bar graph to the potential energy and to the kinetic energy. Notice that the potential energy goes down and the kinetic energy goes up as he comes down the slope. Guess why? As he comes down, what happens to the height? The height decreases, and you know that the potential energy depends on the height, and so the potential energy decreases. And then as he goes, so if potential energy decreases, by law of conservation of energy, we know that it must be converted to some other form, and so the kinetic energy increases. But look what happens to the total energy bar as he goes down and up. Even though the potential gets transformed to kinetic and kinetic gets transformed to potential, the total energy bar remains constant. So in the absence of friction on the slide and air resistance, which are dissipative forces, your total energy remains constant. What happens if there is friction? If there is friction, then some of this energy is going to be converted as thermal or heat energy. So then the total energy will not stay constant, but it will keep decreasing because some energy is dissipated as heat, and eventually the skater will come to a stop. So let's try this. So we can set friction to be some value, and let's put the skater on and see what happens if there is friction. Let's look at the bar graph. Notice as he goes up, the potential energy increases, but the kinetic energy decreases. And for each slide, look what happens to the amount of heat that is generated. And so the heat is going to raise. And since this represents the total energy, not just the total mechanical energy, since this represents the total, which is the sum of the three, that remains the same. But if you look, the total mechanical energy finally reduces to zero when all of this energy gets converted to heat, and that's when the skater stops. So if there is air resistance or friction, then some of the energy is being dissipated as heat. But in the absence of such forces, we can conclude that kinetic plus potential will be a constant. So let's do an example problem on how to apply the law of conservation of energy. So here is a roller coaster as an example, and there is a mass of 50 kilograms at the very top. And we want to calculate the potential, kinetic, and the total mechanical energy at each of these points, and then the velocity and the height at each of these points. So to calculate the potential energy, you would do potential energy is mgh. So it will be 50 times 9.8 times 4, which is the height, and that should be about 1960 joules. And at this point, it starts from rest, so that means your velocity is 0, which means your kinetic energy is going to be 0 joules. So let's put that here, 1960 joules, kinetic energy is 0 joules. So mechanical energy is the sum of potential plus kinetic, so it will be 1960 joules, and the velocity we know is 0 meters per second. Now when we go to position 2, we know one thing for sure, because there is no air resistance or friction, we know that the total mechanical energy at position 2 must be 1960 joules as well. So we know this. And we can find the potential energy because guess what? For 2, we know the height from the reference level, which is 3 meters. So potential energy at this position, again, is mgh, which is 50 times 9.8 times 2, which should be 980 joules. So if potential is 980 and the total is 1960, then you can write kinetic energy as total minus potential. So it is 1960 minus 980, so it is also 980 joules. And if you know the kinetic energy is 980, then we can say 980 equals mass times v squared over 2, which means 50 v squared over 2 equals 980, and that helps us solve for V as 6.3 meters per second. So let's do one more as an example. Let's go to 4. Let's skip 3 for the time being and go to 4. At 4, we know the velocity is 6 meters per second. And therefore, if we know the velocity, what can we calculate? Yes, we can calculate the kinetic energy, which is mv squared over 2. So it is 50 times 6 squared divided by 2. That will be 36 times 25, which is 900 joules. So your kinetic energy is 900 joules. What else do we also know about this position? We know the total mechanical energy is 1960 joules, which means our potential must be 1960 minus 900, which is 1060 joules. And if we know the potential energy, can we solve for the height? Yes, because we know that mass times gravity times height is 1960, and we know mass is 50 times 9.8 times height is 1960, so we can solve for the height as 4 meters. That doesn't seem right according to the diagram, so let's check one more time. So 1960 divided by 50 divided by 9.8, which is 4 meters. So the diagram is so not drawn to scale, but this is what it solves out to be. So let's do one more example problem as practice, where we have a word problem, and let us see how to. Okay, so it says here a 74 kg student starting from rest slides down 11.8 meters high water slide. How fast is he going at the bottom of the slide? So you have a slide here, and here is the student. So we know that the height of this is going to be 11.8, and we want to know what is the velocity at the bottom of the slide. So let's call this as position 1 and this is position 2. We know that the total energy stays the same, total mechanical energy stays the same. So PE plus KE at position 1 equals PE plus KE at position 2. And remember, the formula for potential energy is mgh, and the formula for kinetic energy is mv squared over 2. So we might as well write down the equations so we remember to substitute correctly. At position 1 equals potential plus kinetic at position 2. So now let's substitute the numbers. The mass is 74 times 9.8 times the height of position 1 is 11.8 meters. And then he starts from rest, so that means plus 74 times 0 divided by 2, and then we know that this is going to be, the whole term is going to be 0, equals on this side again 74 times 9.8 times, what is the height at position 2? That's right, it's 0, so this whole thing becomes 0, plus we have the second term, which is 74 times v is what we are looking for, so 74 v squared over 2. So if you see, you can rewrite this as 74 times 9.8 times 11.8 equals 74 times v squared over 2. Well, notice that we can just cancel the mass on both sides. So that means that in order to solve this problem, you don't need the mass. So even if the mass is not given, you could simply write m and m on both sides and then cancel it out. So now if you solve, v squared will be 2 times 9.8 times 11.8 and complete the math, and you will get the velocity as 15.2 meters per second. So to summarize, mechanical energy is potential plus kinetic energy, and in the absence of air resistance and friction, the total mechanical energy stays constant. So in order to solve problems, you just have to set potential plus kinetic at position 1 equals potential plus kinetic at position 2 and then solve it. And in order to solve conservation of energy problems, you sometimes don't need the mass because the mass factor gets cancelled out.